Hello. Welcome to this online presentation of the IEEE Computer article. I am Dhavaleshwar K. Panda from Ohio State University, and I'll be presenting this through a set of slides. And here I'd like to thank our co-authors, Santhan Sir, Shriram Patluri, Krishna Kandala, and Hari Subramani from Ohio State University, as well as Karen Tamko from Ohio Supercomputer Center. Now, what we'll be presenting here is mostly the InfiniBand, and this is a new networking technology which has been gaining a lot of momentums, and over the last 10 years, very many large-scale InfiniBand installations have taken place all over the world. Here it is trying to show in the latest June 2011 top 500 list, there are 206 InfiniBand clusters, almost 41% of the top 500 are now using InfiniBand. Even in the top 30, there are 13 systems installed with InfiniBand. And here it's a short list. It's starting with like 120,000 cores Nebula system in China, which is in the 4th ranked, and the list goes on, and more are also getting installed. So in a very short summary, if we want to capture the communication features of InfiniBand, we'll see there are two forms of communication semantics. One is the channel semantics, which uses two-sided communications like send and receive. And the other one, which is very new with InfiniBand, is called memory semantics. And this utilizes a mechanism called RDMA or remote DMA. And using that, you can do put, that means writing data from the source to the target, or you can do get, where getting the data from the target to the source, as well as you can do atomic operations. And the significant benefit here is that with this RDMA-based communication, you can actually have potential for overlapping computation with communication, and that will be one of the big focus in this research. Now, at the same time, in addition to the point-to-point communication, there has been a lot of work going on with respect to collective communications, and the latest Mellanox Connect-X2 adapters actually provide support for collective offload, which is indicated as code direct, and this also has potential to overlap computation with collective communication. Now here it is a very short slide trying to animate the basic steps involved in the memory semantics of the RDMA put model. So in the left hand side we are seeing like the source processor associated with the memory and the connected to the InfiniBand devices, and there are some queue pair which is represented by QP or CQ, which is completion queue. These are some of the InfiniBand structures I want us to use. And the right hand side we have the receiver. So here you will see that in the beginning the processor has to post a wiki or some kind of a descriptor which contains all the information, whatever is needed to move the data from the source processor's memory to the destination processor memory. And once the processor posts this data or the descriptor to the InfiniBand device, after that the processor is totally free. And then we'll see that the InfiniBand adapter takes this information, and this information contains the send buffer, like from multiple segments, and also the receive buffer, which could be like a single segment. And then the appropriate DMA devices on the InfiniBand adapter actually start fetching the data from the memory, source memory, and directly it goes and gets written to the memory of the receiver. Because this is the RDMA put model, so that means the memory address where the data will be written at the receiver is already known. So that's how it provides a very strong mechanisms to put the data. And at the same time, we'll also get an hardware acknowledgement back from the receiver's InfiniBand device to the source InfiniBand device, and it will also generate a completion queue entries at the source through which the source processor can find out that the data actually got written at the receiver. So broadly here, if you see how it gets done, is the initial processor is involved only to post send wiki and pull out the completed cookie, which stands for CQE from the send CQ, and there is no involvement from the target processor. And this is a mechanism which makes very strong way to overlap computation with communication. Now on the collective side, the similar kind of things takes place. So here it is a an illustration which is trying to show how the multi-send operation, receive followed by multi-send. So that means a node is trying to receive some data, and after that it's trying to send the same exact data to multiple other nodes, and how the latest Mellanox ConnectX-2 adapter with Core Direct supports it. So here, initially the sender creates a task list consisting only send and wait two keys, and the task list can have a lot of operations saying wait, send kind of things in the order in which we want to do the operation. And then and one send key is created for each registered receiver and is appended to the rear of the singly linked task list. And then a wait key is added to make the ConnectX-2 HCA wait for ACK packets from the receiver. So through the animation now we'll see that this task list gets offloaded to the InfiniBand adapter, and in the beginning it waits for the new data to come, and as the data comes the wait gets done, and after that the same data now the adapter can actually keep on sending to the different destinations. So here again the processor is not involved at all. And finally, after that operation is over, it can again, based on the task list, it can wait for the next packet of data to arrive. And then once it arrives, again the wait events gets satisfied and the data gets sent. And finally, you get some kind of an event in the management CQ, and that indicates that the operation has been done. So once again here you will see that this adapter is able to offload the collective support, and the processor is not involved at all after the initiation takes place. And in this context, in this our paper's context, we focus on MVAPICH and MVAPICH-2 software, and this is a high-performance MPI library which has been designed at OSU through many different collaborators, and this is being targeted for InfiniBand, 10 gig IORP, and the new Rocky, which stands for RDMA over Converged Enhanced Ethernet. We have two versions, MVAPICH, which is the MPI-1 compliant, and MVAPICH-2 is the MPI-2.2 compliant, and this project started in 2001, almost when the InfiniBand was emerging. And for the last 10 years, this is very widely used, and currently it is being used by more than 1710 organizations in 63 countries. It is also more than 79,000 downloads have taken place from OSU site directly. And over the years, it is empowering many top 500 clusters. Here are some examples, like the 5th ranked Tsubame cluster at Tokyo Institute of Technology, 7th ranked NASA Pleiades, 17th ranked TAC Ranger. And these MPI libraries are also available with the software stacks of many InfiniBand, high-speed Ethernet, and server vendors, including the widely used OpenFabric's Enterprise Distribution Stack, or called OFED, and also Linux distros like Red Hat and SUSE. And the web page is given here. If you are interested to know more about this project, you are welcome to visit this link. So what in this paper we are trying to do is really focus on co-design. And what we are trying to co-design, we try to take a look at the applications as well as the scientific libraries within the MPI library. So here it shows an illustration of how our co-design takes place. At the very bottommost, if you see, InfiniBand is trying to give you a lot of features like RDMA, offload. It can also be used in terms of a loop-back mode. And especially now the multi-core nodes are emerging, and there also the cores actually talk to each other with shared memory, or it can have kernel-assisted copies, or some nodes can also have an IOAT. So at the very bottommost, we have a lot of these choices, both from the multi-core side as well as InfiniBand side. Now within the MVAPICH-2 library, here we focus on two co-design aspects. One is focusing on the one-sided communication, and we try to see how to co-design that part of the library together with a scientific application called AWP-ODC, which I'll be introducing very shortly. And also we want to also co-design the collective, especially Alltoall, which is one of the most dense collective operation. And here we want to design the non-blocking version of this Alltoall called Alltoall, and also co-designing together with P3D FFT, which is another application. So just to give you a broad overview of this application, AWP-ODC, this is a widely used seismic modeling applications, and it actually runs on hundreds of thousands of cores and consumes millions of CPU hours every year on the TeraGrid. And this is the TeraGrid, which is supported by US National Science Foundation and consists of all the major supercomputer centers inside US. And this application especially uses MPI-1, which is a two-sided communication, and it spends up to like 30% of the time in the communication progress. And since it spends almost 30% of the time, we initially started with our collaborators who have written these applications to indicate that it shows potential for improvement through overlap, and that is the actual kind of co-design here we'll be trying to do. And the right hand side is actually showing a simulation from this AWP-ODC, which has been done by our collaborators at SDSC. And it shows the earthquake simulation in the Southern California region. And the main thing is like if some kind of different earthquake takes place, how exactly it gets propagated in the Southern California region. So this is the kind of simulation which gets done. And here it is tries to go into a little bit more details of this AWP-ODC. So broadly, it is a 3D volume which represents the ground area. And it is decomposed into 3D rectangular subgrids, and this is trying to show a view of the XY plane. And each processor actually performs stress and velocity calculations, and each element is computed from the values of neighboring elements from previous iteration. And there are typically two ghost cells, 2 cells thick, are used to exchange the boundary data with neighboring processes, and using mostly the application uses the nearest neighbor communication. Now here it is trying to show an application pseudocode, and broadly you will see that on the left hand side we have a main loop, then some swapping of velocity data, and then the actual operations are taking place. So we'll see here is that the main loop takes most of the time, that is on the top, and then in the intermediate step we swap the velocity and stress for each dimension, and it is a blocking call, and it waits for completion of each neighbor. And then finally we have the data which needs to be copied into bounce buffers to send the multidimensional data. And how do we expose the overlap in this application? So here basically there are some mathematical expressions here. We are trying to show how we calculate the 3 velocity components and how we calculate the 6 stress components. And each property has actually multiple components, and each component corresponds to a data grid. So it is to be noted that computation of one component is independent of the others, but however there are data dependencies between the stress and velocity. Now what we tried to do, as I indicated earlier, this application was written with MPI two-sided communication, that is like MPI-1 compliant. So here we wanted to see how we can co-design it together with our MVAPICH library to rewrite the applications using MPI-2 RMA, that is the remote memory access operations, and at the same time we also wanted to redesign the MPI library to have this RMA support. So the equivalent code is shown here. In the beginning we have some MPI win post operation. Here it pre-posts some windows which combine the different dimensions U, V and W, and then the post starts and then issues some non-blocking MPI put, and then the issue completes and waits to finish, and that's how the operations can be done. Now here we wanted to really exploit how to see that we take care of the overlap to the fullest extent. Now the limiting factor may come not just from the network side but also from the multi-core side, and as I indicated earlier, like there are different kinds of shared memory communication takes place, and nowadays multi-core systems are becoming very common. Currently you can get platforms with 8 or 12 or 16 or 24 cores. In fact, some new systems are emerging with 32 and 64 cores. So depending on the data distribution and communication characteristics, there could be a significant amount of communication happening within the node, that means not outside. So in the AWP-ODC, communication with neighbors in one dimension will always be within a node. So that is almost like 1/3 of the communication. So here again we ask the question saying, in addition to the overlap on the network side, can we also provide overlap here within the node? So the next slide here, it's trying to show how we can overlap the intra-node communication. So broadly the figures are showing the difference between two mechanisms. One is a pure shared memory based communication, which is like the blue line, and another is the loopback, which is the red line. So the loopback basically doesn't use the shared memory within the node, rather it goes to the InfiniBand adapter and the data gets looped back. So obviously you can see that when we take the latency operation or latency measure, you will see that the shared memory is always good, but loopback is not good. But if you take we modified this benchmark to introduce some computation internally. Okay, so instead of just doing a ping pong latency, we wanted to put some computation inside, and here we saw very different kinds of results, and that's what is being shown on the right hand side. So we introduced 200 microseconds of computation inserted, and now you can see that with loopback we are able to get very flat latency, whereas the shared memory communication, the performance degrades, because in the shared memory communication the actual cores are used to copy the data, and so once we insert computation, then that gets degraded. On the other hand, if it is a loopback, then the network is trying to do this copy, so we are able to really overlap the computation with communication, and that's what is indicated in a bulleted form here. The shared memory communication is a copy-based scheme which gives better performance but poor overlap. However, as modern interconnects like InfiniBand, which provide loopback, and these are primarily DMA-based scheme, so they give lower performance, but they provide also very good overlap. And this can be used for overlap to hide communication latency completely. And also, like the platforms have IOAT, they also can be used to obtain the similar effect. So here we are showing some experimental results for our application. So the left hand side you can see it's a total execution time. We used 128 by 128 by 128 data grid per process, and this experiment was run on a 48 core environment that is on the Magni core system, that is the graph on the left. And here you can see that the computation is the blue part, which is more or less remaining the same when we run either with the shared memory or with the loopback, but the actual communication time, which is around 132 seconds when using the shared memory, we are able to totally reduce to 0 using the loopback approach. And the right hand side graph shows the results we took on the TAC Ranger system. This is one of the very largest InfiniBand cluster available for open science research. We ran this on 8,000 cores, and here we considered these three schemes, like the original code versus our one-sided design, and then combining one-sided with the loopback. And as you can see that we are able to reduce the time from 113 seconds to 96 seconds, so which is almost like 15% improvement in the execution time. So now let's move to the collective communication side, and I showed the basic animation of how the collective things work, and here let's try to go into a little bit more detail, saying how we can design some good collective communication primitives with offload support. So here in a pictorial manner we are trying to describe the common operations which takes place mostly in the MPI, like one-to-many or many-to-many or reduce, those kind of operations. So here we have introduced a set of primitives to help in designing these collective operations. So the top one is saying one-to-many multi-send. So that means if the adapter has a copy, how it can actually send the data, that particular data, to multiple other receivers. Or you can do a multi-receive, that means how to receive data from multiple adapters to the same node. Or you can do a receive reduce, so that means you first get the data from several nodes, but you can do actually some reduction operation, in this case let's say summation, or you can do a max, min, those kind of operations. Or in case you can even go and try to do some more complicated operations like receive replicate. So that means at a given node we try to receive from one node and then try to replicate it to the other nodes. And other collectives can be designed with this kind of primitives. So these are some fundamental ones. If we can design this, then the other collectives can be built on top of these ones. So in the context of co-designing together with the offload, we chose this parallel 3D FFT application kernel. And these applications in direct, they are used in applications in direct numerical simulations, astrophysics, material science. So all these applications rely heavily on 3D FFT kernels. And the transpose operation exchanges a total amount like n cubed by p data elements. And people have already shown that this is very sensitive to the network bandwidth. And here we did some earlier analysis, and we saw that it takes up to 50% of the overall execution time. So that means this application is very hard to scale. And in this case, we use the P3D FFT, which is a 3D FFT library developed at the San Diego Supercomputer Center, and uses a basically 2D pencil decomposition, which improves performance at scale. So here the goal was that how we can utilize our Codesign approach to redesign this P3D FFT library with offloaded Alltoall. So the goal is again just similar to the point-to-point one-sided communication we saw earlier. Can we hide the costs associated with the heavy all-to-all operations with collective offload? Here the forward and backward transform pages operate on independent variables at a time. So that means we can actually hide the latency of the transport pages by overlapping all-to-all communication with computation of different variables. And if we can do that all-to-all based on the collective offload, that gives us a lot of flexibility to carry out this overlap. So here it is trying to show a very pictorial manner how we went ahead with designing the scalable offload all-to-all. So here it is trying to show on the left-hand side there's an application thread, and we have designed an also offload progress thread. So after we do the MPI init, the application does the MPI all-to-all, and that actually creates a task list and then posts it to the offload progress thread. And there actually it posts the list, it initiates different kinds of InfiniBand events, it triggers the post list, and then finally the end of the list, like all the operations get done, and that particular thread then sends a message like the all-to-all complete thread, complete operation signal to the application thread. And here you can see on the left hand side, since while the all-to-all is taking place, we should be able to insert our computation there and finally come and do this MPI wait. And if we can do that, then we can get significant overlap between the all-to-all operation, whatever is taking place, with the offloaded adapters, and then the actual processors are busy in doing the computation. So here it shows a little bit more in an animation form how we try to do the P3D FFT for overlap. And here there are like different colors. So one is the 1D FFT along a dimension, that's like the pink, and then the other one is trying to show how we do the transpose operation. And initially we try to carry out these things within the intra-node, and then after that we take care of the inter-node. And with respect to the timeline, so here it is showing how we do FFD like along x direction first, then we try to do a transpose into xy, then we do FFT along the y dimension, then we try to do the transpose in the y and then part of the g dimensions. So like this, we can actually try to overlap some of this computation while the communication is taking place. So here you can see that there are two parallel transpose operations are happening together, and like this, the things can get continued. And if you see the timelines compared to the top and to the bottom, we are exactly trying to do the exact same things. Like we have not changed anything. The same amount of computation is being done. But now since we are able to overlap the computation with communication, the total time, that is the x-axis, is significantly lower than that of the top one. So here let's take a look at the performance numbers, and here it shows like this is a all-to-all latency comparison on 256 processes, and the x-axis is for different message lengths starting from 16K to 1 megabyte. And we have three lines here. One is a all-to-all default host, that is the dark line, and the all-to-all with offloaded version, that is the red one. So purely from a latency perspective, you will see that more or less we do the similar. There is a little bit of additional overhead with the all-to-all, especially when the message sizes are large. And here also we compared an all-to-all with a non-blocking version, which is a host-based version in the literature known as libNBC. That is the non-blocking collectives library, which has been designed by other researchers. So we try to also compare that. And here you can see that the all-to-all libNBC version doesn't do that well because it's a host-based, and you cannot really overlap a lot of computation when you are trying to make the progress at the host level itself. So all-to-all offload here delivers very good overlap without sacrificing on the communication latency, and at the same time it can also provide us the to overlap and then scale the application. And the next slide here, we clearly see the benefit. This is like the parallel 3D FFT. This is we are running our co-designed version where we modified the applications to have the overlap, and also we are trying to run it on our offloaded adapters. And here we are trying to show the results on 128 processes for different problem size. That is the matrix dimension we are talking about. And there is like the blocking version, that is the purely host based, what is available out there. And then this is the edge test, which is because of the libNVC version where we perform some changes, and the red one, which is the offloaded version. And clearly you can see that the P3D FFT with offload I2All performs about 13.5% better than the default, and both the P3D FFT and about 12% better than the P3D FFT with host based test. That is the non-libNVC version. So we are able to really take advantage of the overlap to get the maximal benefits here. So to conclude the presentation, so what we tried to do it in this paper, that in the MVAPICH library takes advantage of the modern IB features for MPI-2 RMA operations, as well as loopback intra-node communication and collective offload. And at the same time, the applications are very data intensive. And what we try to do here is that can we actually do the co-designing, and that was the main focus here. And we co-designed together with the MPI-2 RMA operations and loopback intra-node communication to reduce the execution time and provide scalability. And we also demonstrated that scientific libraries like P3D FFT can be co-designed with the MPI library with offload capability. And currently we are carrying out scalability studies with offload for a larger cluster. And also we have a plan in our open source MVAPICH release to add this collective offload support in the future. So for more information on our project, there are some web pointers on my web page, as well as the project web page, and these are all our email addresses. So if you have any questions, please feel free to contact us. And I hope you enjoyed this presentation. Thank you.